This lecture is on weather analysis and forecasting. The United States government agency responsible for gathering and disseminating weather-related information is actually the National Weather Service. And the National Weather Service is a branch of the National Oceanic and Atmospheric Administration. The mission statement of the National Weather Service is to provide weather and climate forecasts and warnings to the United States. And this include thunderstorms, floods, hurricanes, tornadoes, winter weather, and extreme heat to the U.S. territories and waters for the protection of life and property, and also enhancement of the economy. Now, the first phase of forecasting involves the complicated and detailed process of collecting and assimilating weather data on a global scale. In the United States, this formidable task is performed by a division of the National Weather Service, which is called the National Centers for Environmental Prediction, NCEP, which is actually located in College Park, Maryland. Now, the NCEP is also responsible for disseminating information to 122 regional weather forecast offices, which prepare local forecasts. Now, for us here in Youngstown, our National Weather Forecast Office is located in Cleveland. This is a partial organizational chart for National Oceanic Atmospheric Administration, and it shows the relationship between the parent organization, which is NOAA, and the National Weather Service branches responsible for collecting and analyzing weather data, as well as producing and disseminating weather forecasts. So you can see the National Weather Service has different branches. There's the National Centers for Environmental Prediction. Within the National Centers for Environmental Prediction, there's Climate Prediction Center, Environmental Modeling Center, Weather Prediction Center, National Hurricane Center, and Storm Prediction Center. Now, the World Meteorological Organization, which is part of the United States, is actually responsible for international exchange of weather data. The task requires that data from more than 185 participating nations, as well as 6 territories around the globe, be collected simultaneously, standardized, and transmitted to the participants. There are many service observations that are being used. The National Weather Service and the Federal Aviation Administration, FAA, operate approximately 900 automated service observation systems, ASOS. Worldwide, there are more than 10,000, in fact, around 11,000 land observation stations, more than 4,000 ships at sea, and hundreds of data buoys and oil platforms. They report conditions 4 times a day. Now, this is what is called the automated service, automated observing systems. They are equipped with a variety of instruments that are designed to sample the sky for cloud coverage, take temperature and dew point measurements, determine wind speeds and direction, and even detect present weather, such as is it raining or is it snowing. Because weather systems are three-dimensional, upper air observations are essential for producing reliable forecasts. Radio zones, are primary tools that are being used to gather weather data aloft. These lightweight instruments packages, which contain sensors to measure temperature, humidity, and pressure, are carried aloft by weather balloons. So you can see right here being released, and they are carried by weather balloons. The data is transmitted to a local observation station that launch it, usually a weather forecast office in our region, Cleveland. And so worldwide, about 1,300 radio zones are launched twice a day. So they are aloft at approximately 0000 and 1200 coordinated universal time, also known as the Greenwich Meridian Time. In addition, there are about 4,000 aircraft reports on atmospheric conditions aloft, mainly temperature and airflow data during flight. One of the first amounts of observational data is collected. Once this data is collected, it's displayed on a series of computer-generated weather maps. And so the collected information is displayed in a format that can be comprehended easily by forecasters. So to the trained eye, these weather maps provide a snapshot of the surface conditions, including temperature, humidity, wind, and cloud cover, as you can see with this map here. So the information is placed on a synoptic weather maps, which means coincident in time. Upper level charts are generated twice daily. So you can see here, we have a chart close to the ground, another chart around 850 millibar, 700 millibar. So as you increase altitude, pressure decreases. So we have these heights based on the atmospheric pressure. So these maps or charts are drawn at 850, 700, 500, and 200 millibar pressure levels as height contours in meters or tens of meters. There are 850 and 700 millibar charts. So you can see 850, 700. For 850, the 850 millibar map finds areas of cold air, warm air advection. Advection means horizontal movement of air. So the example you see here, it's an 850 millibar map showing height contours using solid black. So when you see this solid black, these are height contours at 30-meter intervals. So you can see 1470, 1500, 1530. This is where the 850 millibar heights are located. There are also dashed red isotherms labeled in degrees Celsius. So these red dotted lines are temperature lines. And wind data are plotted using black flags. So you can see the winds here, the wind speeds up in that 850 millibars. And if relative humidity is included, humidity levels above 70% are indicated in shades of green. So here is where we have more humidity or more water vapor. So forecasters, they regularly examine this 850 millibar map to locate areas of possible cold air or warm air advection. Cold air pushing south, warm air pushing towards the north. Also, temperatures at 850 millibar level provide other useful information. In winter, for example, forecasters use the 0 degrees Celsius isotherm. So for example, here if you see the 0 degrees isotherm as the boundary between areas of rain and areas of sleet or snow. Looking at the 700 millibar chart, winds at this 700 and 700 millibar level are used to predict movement of weather producers. So this is approximately at 700 millibar, this is approximately 2 miles from the sea level. And it serves as the steering mechanism for ordinary thunderstorms that tend to occur in the warm summer months. And therefore, winds at this level are used to predict the movement of these storms. Looking at the 500 millibar height, and this 500 millibar is found approximately 5 kilometers or 18,000 feet above the sea level. So you can see here. And in this particular map, you see there's a large trough. So you can see there is a ridge and a trough. A trough is like a valley, and this is a ridge. So there is a trough, a large trough that occupies eastern United States, whereas a ridge is influencing the western United States. Troughs, they indicate the presence of a storm, so you can see this trough at mid-tropospheric levels, whereas ridges are associated with clear, dry weather. So our forecast predicting that a trough will increase in strength is an indication that a storm is likely to intensify. So forecasters, they find these 500 millibar charts useful tools for estimating the movement of surface cyclonic storms. And these important weather producers tend to travel in the direction of airflow at 500 millibar level, but roughly a quarter to half the wind speed. At 300 and 200 millibar heights, so this is 300 and 200 millibar heights, these are the levels at which the details of the jet stream can be observed. And so they actually represent the levels at which they actually represent zones near the top of the troposphere. Occasionally, the flow within the westerlies, so westerlies means winds moving from the west to the east, as in the case of our region, is directed along relatively straight path from west to east, and this pattern is referred to as zonal. So zonal patterns depict quickly moving westerlies, winds moving from west to east. So storms embedded in zonal flow move quickly across the country, particularly in winter. This situation results in rapidly changing weather with periods of light to moderate precipitation followed by brief periods of fair weather. More often, however, the flow aloft consists of long waves, troughs, and ridges, as we just saw in the previous slide, that have large components of north-south, and in this case, north-south is actually what is called the meridional patterns. So they do have that north-south flow. So typically, these airflow patterns slowly drift from west to east, but they occasionally stall and may even reverse direction. So as these wavy patterns gradually migrate eastward, cyclonic storms embedded in the flow are carried across the country. So what you're seeing here is the movement and intensification of an upper level trough. So you can see trough is here moving towards the east over a 4-day period from January 1st to February 4, 2000 and from February 1st to February 4, 2003. And this right here, this surface map shows strong cyclonic storm that formed earlier in the week and moved in conjunction with the trough to the position shown here. Okay. Now, this right here is precipitation map showing precipitation amounts that fell from 7 a.m. February 4th to 7 a.m. February 5th. Until the late 1950s, all weather maps and charts were plotted manually and served as the primary tools for making weather forecasts. Today, however, we use computers to plot data and produce weather maps. Our computers have actually improved the accuracy and detail of weather forecasting and have lengthened the period for which useful guidance can be given. So there is what is called numerical weather prediction, and it's a technique that employs complex computer programs called forecast models to make a weather forecast. Numerical weather prediction relies on the fact that the behavior of atmospheric gases is governed by a set of fundamental physical principles or laws that can be expressed as mathematical equations. And so meteorologists begin by plugging current atmospheric conditions such as temperature, pressure, and wind into the forecast model and run this on supercomputers. Now, the National Weather Service utilizes several different numerical models, including global and regional forecast models. It begins by, or they do begin by this numerical prediction method. Numerical data forecasting begins by assigning the current weather measurements, temperature, wind speed, humidity, and pressure to each of the points in the forecast model. And next, a computer simulation solves each equation for as many as 50 levels of the atmosphere. With these, a model outputs statistics, so once generated, statistical methods are used to modify machine-generated numerical forecasts by making comparisons of the accuracy of previous forecasts. And so this approach is what we call here the model output statistics. Now, using various mathematical models, the National Weather Service produces a variety of forecast charts. And because these machine-generated maps predict atmospheric conditions at some future time, they are often referred to as prognostic charts or simply progs. There's also what is called the ensemble forecasting, and this method produces a number of forecasts using the same computer model. So one of the most significant challenges for weather forecasters is the chaotic behavior of the atmosphere. Specifically, two similar weather systems may, over time, develop into very different weather patterns. And so, to deal with the inherent chaotic behavior of the atmosphere, forecasters, they rely on a technique which is called ensemble forecasting. Simply, this method involves producing a number of forecasts using same computer model, but slightly altering the initial conditions while remaining within an area of the observational instruments. And so one of the most important outcomes of ensemble forecasts is the information they provide about uncertainty. Although computer-generated prognostic charts form the basis of modern forecasting, other methods are available to meteorologists. And this include persistence forecasting. There's also what is called climatological forecasting, an analog method, and trend forecasting. In terms of persistence forecasting, this is based on the tendency of the weather to remain unchanged for several hours or even days. So for example, if it's raining at a particular location, it's reasonable to assume that it will still be raining in a few hours. So persistence forecasts do not account for possible changes in the intensity or direction of a weather system, nor do they predict the formation or dissipation of storms. The other type of forecasting is what is called climatological forecasting, which is relatively simple way of generating forecasts using climatological data. Here, I mean, average weather statistics accumulated over many years. For example, if we say Youngstown experiences sunshine approximately 70% of its daylight hours. Therefore, forecasters predicting sunshine every day of the year would be correct about 70% of the time. One way that they have used, in fact, they have used this particular, one interesting way they have used climatological data is for predicting a white Christmas. And this is a Christmas, this means that is a Christmas with an inch or more of snow on the ground. There is also what is called the analog method, and this is based on the assumption that weather repeats itself in a predictable way. Thus, forecasters attempt to find well-established weather patterns from the past that are similar to the current. So from such a comparison, forecasters predict how the current weather might evolve. And the analog method was the backbone of weather forecasting before the advent of computer modeling and the analog method. There's also what is called the trend forecasting method, which involves determining the speed and direction of features such as fronts, thunderstorms, and areas of precipitation. Using this information, forecasters attempt to extrapolate the future position of this weather phenomena. For example, if a line of thunderstorm is moving northeastward at 35 miles per hour, a trend forecast would predict that the storm will reach a community located 70 miles to northeast in about 2 hours. And so, because weather events tend to increase or decrease in speed and intensity or change direction, trend forecasting is most effective over periods of just few hours. So it works particularly well for forecasting severe weather events that are expected to be short-lived, such as hailstorms, tornadoes, downbursts, because warnings for such events must be issued quickly and must be site-specific. So now let's look at tools in forecasting. And in this case, we are going to talk about the weather satellites. Meteorology entered the space age in 1960 when the first weather satellite, TIROS-1, was launched. This satellite, like other weather satellites in this series, was placed in a polar orbit so that it cycles the Earth from roughly north-south. So these are called the polar orbiting satellites. There are also some satellites that are known as geostationary or geostationary operational environmental satellites, or GOES, and these instruments remain fixed over a point on Earth because their rate of travel keeps pace with Earth's rate of rotation. In order to remain positioned over a given site, however, the satellite must orbit at a greater distance. And in this case, most geostationary weather satellites are placed, or they are around 22,000 miles. That's where they are positioned, 22,000 miles away from the Earth. So you can see from these two diagrams, this is how polar orbiting satellites, where they are located and how they move, while for the geostationary satellites, they're actually positioned at almost same location. It doesn't move, or it moves with the rotation of the Earth. So the most recent generation of weather satellites provides visible, infrared, and water vapor images. So these geostationary operational environmental satellites do provide visible, infrared, and water vapor images. The GOES 16 is actually the most recent generation in the core series. It was launched in 2016. So for the visible images records the intensity of light reflected from cloud tops and other surfaces. And these images are similar to black and white photos. And they only operate during the day. So it's like you flying up in a plane and looking down. If it's dark, you're not going to see anything. During the day, you're going to see because of the reflection of light. So clouds or snow and ice-covered areas have high albedos, so they are going to reflect highly and thus have strong reflectors of light. Thick clouds appear bright white, while thin clouds are dull white. Land surfaces appear dark gray because they reflect less light than clouds, whereas oceans will reflect very little light and they appear black. And so visible images are useful in identifying also cloud shapes, organizational patterns, and cloud thickness. In general, the thicker the cloud, the brighter it appears in the image. Cumulonimbus, for example, clouds have a bumpy appearance, whereas stratus clouds, they form a continuous flat-looking blanket. For the infrared images, they are usually generated by computers programmed to display warm objects such as Earth's surface in black and colder objects such as iCloud tops in white. So because iCloud tops are colder than low cloud tops, towering cumulonimbus clouds that usually generate heavy precipitation usually appear very bright, whereas mid-level clouds appear light gray. Low fair weather cumulus clouds, stratus clouds, and fog are all relatively warm and therefore appear dark or may not be discernible on infrared images. So in this map here, you can see this is a visible light image provided by the GOES, GOES satellites from midday on July 15, 2011. It records sunlight reflected off various Earth surfaces, as you can see here, and appears much like black and white image. So wherever you have bright areas, these are usually clouds. And if we zoom into this area around Iowa, close-up visible image, you can see the towering cumulonimbus clouds with overshooting tops. So these are the differences between visible and infrared. Visible can be used only during the day or useful during the day. Infrared, you can also day and night. The visible images are usually have higher resolution, and they don't represent temperature. It's just the reflected energy. For infrared, they show temperature of cloud tops. Lower clouds are warmer. Higher clouds are actually cooler. The other type of image that can be derived from GOES satellites is water vapor images. And most of Earth's radiation with a wavelength of 6.7 micrometers is emitted by water vapor. So satellites are equipped with detectors for this narrow band of radiation, and they are used to map concentration of water vapor in middle and upper troposphere. So the bright white areas, as you can see here, represent regions of high water vapor concentration, whereas the dark areas indicate drier air. Because most fronts occur between air masses having contrasting moisture conditions, water vapor images are actually valuable tools for locating frontal boundaries. Now, because many disasters are weather-related, probability, the most significant professional contribution of a forecaster is issuing a forecast or warning of an impending severe weather event. Now, most forecasts are one of the two types, either qualitative or quantitative. For a quantitative forecast, this describes an aspect of the weather that can be observed but not easily measured. So you'll hear a forecast saying partly cloudy in the morning followed by gradual clearing. Or we are expecting gusty winds this morning. That's qualitative forecast. On the other hand, quantitative forecast deals with measurable weather data. An example is a forecast predicting the maximum and minimum temperatures of the day, or the amount of precipitation that we expect to fall in Youngstown on a certain day. Now, the tools that forecasters use depend largely on how far into the future the forecast extends. The National Weather Service defines weather forecasts based on time. For example, short-range forecasts extend up to 48 hours or 2 days. Medium-range forecasts cover periods extending about 3 to 7 days into the future, while long-range forecasts are for periods beyond 7 days and have no outer limit. At the very beginning of this lecture, there is something that we probably touched on. It's called nowcasting. And this is the shortest forecast period. It extends to up to 6 hours. So there's something called nowcasting. Long-range forecasts extending to 2 weeks are generated by the Climate Prediction Center. And the Climate Prediction Center is also responsible for producing monthly and seasonal 3-month weather maps for temperature and precipitation called 30 and 90-day outlooks. If we look at this map here, it shows, or these two maps, they show temperature and precipitation 90-day outlooks issued for September, October, and November 2011. The temperature outlook that you see here calls for warmer than usual conditions across much of the southwestern, much of the north central, and much of the northeastern United States. The remainder of the country is labeled equal chances, and which indicates that there are no climatic signals for either above or below normal conditions during the forecast period. In regards to the precipitation outlook, this calls for weather than normal conditions across most of Kansas, Nebraska, and South Dakota, whereas drier than normal conditions are expected in portions of southwest from Texas to southwest to southeastern Arizona. And so these outlooks are really important for giving us an idea of what might happen in a month, 2 months, or 3 months. The National Weather Service issues watches and warnings to alert the public about potentially dangerous weather. A watch means that conditions are right for hazardous weather development and that residents should be aware and ready to act. A warning, though, means that dangerous weather has already developed and has been observed in or is moving towards the designated area. For severe thunderstorms, tornadoes, flash floods, events that quickly develop, response times are usually very short, and so taking immediate shelter is strongly recommended. The Storm Prediction Center, which is located in Norman, Oklahoma, has the primary responsibility for forecasting severe weather such as thunderstorms, tornadoes, hail, lightning, and whenever possible, outlooks for areas that might incur severe weather are issued a day prior to anticipated events. And so this Storm Prediction Center then works with the local forecast offices of the National Weather Service that are equipped with weather radar to monitor severe weather events as they develop. The tracking and monitoring tropical storms and hurricanes in the Atlantic, Caribbean, and Eastern Pacific is the task of the National Hurricane Center, which is located in Miami, Florida. And so an important focus challenge for the National Hurricane Center is population growth along the Gulf and the Atlantic coast, with some areas requiring a 24-hour warning for evacuation. So what's the role of the forecaster? Now, the National Weather Service provides a local forecaster with the observational data, satellite feeds, numerical models, and outputs, and the various weather maps discussed earlier. And so forecasters at the local weather forecast offices are responsible for modifying numerical predictions by taking into account local conditions and nuances to produce site-specific forecasts. And so one local condition that forecasters must consider is the existence of microclimates, different climatic zones within a relatively small area. There are some forecasting tools. There's what is called Advanced Weather Interactive Processing System. And so to aid in the enormous task of weather forecasting, local weather forecast offices are equipped with an interactive computer system called the Advanced Weather Interactive Processing System, AWIPS. And so information, or AWIS, is an information processing, display, and communication system that integrates all models and observational data, including satellite and radar data, in one location. These particular AWIPS workstations consist of 3 graphical displays and usually 1 or 2 or more personal computers for interacting with the text materials. Our forecasters use this system to analyze and integrate the following data types. And these data types would include, for example, numerical weather forecast products, Doppler radar displays, GAUSS data or geostationary operational environmental satellites data, the service data from an automated service observation system or observing system, forecast guidance products from the National Hurricane Center, the Storm Prediction Center, the upper air sounding from radio zones launched at nearby sites, service weather maps, and upper charts. And there are usually multiple AWIPS systems found in each local weather forecast office. So once forecasters are confident in their modification to the original guidance, the computer system automatically creates all the forecast products. In addition to the text forecast, the system produces an entire suite of forecast graphics accessible via the internet. The other forecasting tool is what is called a thermodynamic diagram or thermodynamic diagrams. And so this, the observational, these graphs, which are called thermodynamical diagrams, they're usually associated with the upper level data from the radio source. And they provide a vertical profile of the temperatures, dew point temperatures, and wind through the atmosphere for a particular time and location. So these are just 2 of many forecasting tools. And this concludes this lecture on weather forecasting and weather analysis and forecasting.